Hi, ladies and gentlemen. I wanted to go over Newton's laws notes with you today. So the first Newton's first law of motion, is otherwise known as the law of inertia. Now, what this means is that an object at rest will stay at rest, and an object in motion will stay in motion or at the same velocity unless it's acted upon by an outside force or an unbalanced force of some kind. Now, inertia is the tendency of an object to resist changes in motion. So the greater the mass of the object, the greater the inertia, and the more it'll be able to resist those changes to its motion. So a good example here, inertia, when your truck has brakes, the massive hunk of stone doesn't. So this truck had this large piece of stone sitting in the trailer here. It was moving along the road. So both objects, the truck and the stone, were both moving. When the truck hit the brakes, the truck slowed down, but the stone, having so much mass and therefore so much inertia, resisted that change in its motion and wanted to keep on moving forward. And it seems to have crushed the truck. Now, Newton's first law of motion continued here. So, our first example of inertia, a person is moving in a car and the car comes to an immediate stop. Now, most of us have probably been in a similar situation. What happens is you're going to stay in motion. You're going to get pulled forward, and that seatbelt will catch you. That's the whole point of the seatbelt there. Now, our second example, so a car with a person inside accelerates quickly forward. So this is like when you're getting up to speed on the highway or the light turns green and you start moving in a hurry. All right. Well, what happens to the person inside? Well, instead of getting thrown forward this time, you're going to get pushed back against the back of the seat. So you're going to want to remain at rest. You're trying to stay where you are and the car is moving around you. That's why we have headrests. Without headrests, your neck could get jerked violently backwards and it could injure your neck. This YouTube video has been linked to your notes in your digital notebook. Please check it out there. Now, Newton's second law of motion is the law of acceleration. Now, this can be summarized as an unbalanced force accelerates an object in the direction of the force in proportion to its mass. So, bigger force or smaller mass is going to mean a greater acceleration. The formula we use for this is force is equal to the mass times the acceleration. F is the force, A is the acceleration, and we already know m to be the mass. Now this is our equation triangle right here. If we're trying to solve for something other than force, we cover up that thing in the triangle and see how the other two variables are situated next or around each other. So if we're trying to solve for mass, we cover up mass, and we'll see that force is over acceleration. So we do force divided by acceleration. If we're solving for acceleration, we cover up acceleration and do force divided by mass. So our first example problem. A 30 kilogram box is accelerated 2 meters per second per second. What is the force needed to move the box at the given acceleration? So we know the mass of the box and we know the velocity, or excuse me, the acceleration of the box, and we're looking for the force. So we know force is equal to mass times acceleration. Our first step is going through and identifying what the question gives us. We've done that right here. We set up the equation we want to use. Then our third step is we plug the variables into the equation. Now, when we do this, we can now just multiply these two values together and get our force of 60 newtons. Now, guys, force will always be measured in newtons for us. You can also measure force in pounds, but when you're multiplying kilograms in meters per second squared or meters per second, you will end up with newtons. Now, Newton's second law, our second example. Gina applies a force of 35 newtons to a box with a mass of 20 kilograms. What is the acceleration of the box? So now we're solving for something other than force, which means we're going to have to set up our equation a little differently. First step is we go through the question and identify what it gave us. So it gave us a force, and a mass in the question. The force was 35 newtons, mass was 20 kilograms, and the acceleration is what we're solving for. So we're going to set up the equation to be acceleration is equal to force divided by mass. Next, we'll plug those values into the equation. So 35 divided by 20, and that's going to give us 1.75 meters per second, or meters per second squared, however you prefer to write those units. Difference between mass and weight. Now, mass is the amount of matter in an object. This is generally going to be measured in kilograms or sometimes grams. Well, weight is the force of gravity pulling downward on that object. Weight is a force that's going to be measured in newtons for our purposes, but we commonly measure it in pounds. Now, our equation for weight is very similar to Newton's second law equation. It's weight is equal to mass times gravity, where gravity is taking the place of acceleration and weight is taking the place of force. Now, the thing with this equation is that g has a very specific value on Earth. G will always be equal to 9.8 meters per second, or meters per second squared. Now, that is true for everywhere on Earth. Now, if you go to a different planet, you'd use a different g value, but otherwise, for our purposes, g will always be this value right here, 9.8 meters per second squared, or meters per second. All right, so here's a comparison of mass and weight on Earth and the Moon. Doesn't matter where you go, if you're on Earth or on the Moon, your mass will remain the same, but your weight is going to change because that is affected by the gravity of that planet that you're on. On Earth, we have more gravity, or greater acceleration of gravity, than we do on the Moon, so your weight would be different. Here we see we have a weight of 1,200 newtons, while on the Moon you have a weight of 200 newtons. So our weight and mass problem, number one, this is still using Newton's second law. An object has a weight of 85 newtons. How much mass does it have? Now, we know the value of g and we know the weight here, so we're looking for the mass. So our force is 85 newtons, our acceleration is 9.8 meters per second, and all we need to do is find the mass. So we set up the equation to be mass is equal to force divided by acceleration, and we plug in the values. 85 newtons divided by 9.8 meters per second. And when we divide, it should give us 8.67 kilograms as the mass of our object. Newton's third law of motion is otherwise known as the law of momentum. Now, what this means is that for every action force, there's an equal but opposite reaction force. All forces come in pairs. It's important to note that these pairs act on opposite objects. So, walking will come in pairs, your foot pushing the ground pushing back on the foot. Rockets push the fuel out, the fuel pushes back on the rocket. Jumping out of a boat, when you jump out of a boat, you jump off the boat pushes, or you push off the boat pushes off on you, and you both go in opposite directions. If you've ever tried that with a pool raft, don't. It's a really good way to hurt yourself. Momentum is conserved. So that's the other thing. Momentum is a constant value. It's not going to go, or it's going to generally be conserved throughout the situation. We'll talk more about that as we move forward. Now, momentum is the product of mass times velocity of an object. So our equation is P is equal to M times V. P is our momentum variable, V is velocity, M is mass, all right? Here's our momentum triangle here. If you're solving for P, or momentum, you do mass times velocity. If you're solving for mass, you do momentum divided by velocity. And if you're solving for velocity, you do momentum divided by mass. Problem number one. What is the momentum of a cart that has a mass of 8 kilograms and a velocity of 20 meters per second south? Well, first our first step is to identify what the question gave us, so we know the mass and we know the velocity. Then we're going to identify the equation we're going to use and then plug those values into the equation. 8 kilograms times 20 meters per second will give us a momentum of 160 kilogram meters per second south. Now, momentum is a vector quantity, so it does need a direction. All right. So the total amount of momentum in an isolated system is conserved. In other words, for every action, there is an equal and opposite reaction. So here's our scenario here. Vehicle A, with a mass of 6,000 kilograms, is traveling at 40 meters per second north. What is the momentum of vehicle A? So again, we're just going to multiply our mass times our velocity. Step one. We identify our equation, and we multiply those two values, and we get our momentum of 240,000 kilogram meters per second north. All right. So we're gonna hang on to that value here for a second as we continue calculating this scenario. So vehicle B here, with a mass of 2,000 kilograms, is traveling at 40 meters per second south. So what is the momentum of vehicle B? Well, again, we identify the variables we're given, identify the equation we're going to use, plug the values into the equation. So 2,000 kilograms times 40 meters per second. And when we multiply these two values, we get 80,000 kilogram meters per second south. So those are our two values. Now, what would happen, or what would the momentum of vehicle A and vehicle B be after the collision? So what we're going to do is we're going to take the momentum of A, subtract it from vehicle B, or subtract vehicle B's momentum from that, and that'll equal our total momentum. So just like when we added and subtract vectors, because these are in opposite directions, because they're meeting head on, we're going to subtract these values. So this is just simply vector addition at this point. So we're going to subtract these two values. We have 240,000 minus 80,000, and it's going to give us a total momentum of 160,000 kilogram meters per second north. Keep in mind, this is going to go in the direction of the larger momentum. And the little ride in the bigger truck. If you're in a car accident, you don't want to be in the smaller car for this reason right here. It's because momentum is conserved. All right, ladies and gentlemen, that concludes our notes for today. I hope you guys have a great day, and I will talk to you guys later.